We're going to continue talking about some elementary properties of complex numbers so that we'll be able to get a good start the next day on using them to help solve differential equations. Here's some other interesting and relevant things about complex numbers that you should know. If we start with a complex number, z is a plus ib, we have what we call the complex conjugate, which we write as z bar, which is just a minus ib. You just change the sign of the imaginary part. Then we define what we call the modulus, it's written like an absolute value because you can think of this as the distance of the number from the origin in the complex plane, which we'll talk about in a few seconds. The square of the modulus is z times z bar, and if you write down a minus ib times a plus ib, that product has real part, which is a squared, that's a times a, plus b squared, because ib times minus ib is plus b squared. But the imaginary part is ab times I and minus ab times I, which cancel. So z times z bar will give you a real number, a squared plus b squared, and that will be the square of what we call the modulus of z, so that the modulus of z is just the square root of a squared plus b squared. I talked about the complex plane, so let me describe that to you here. When we talk about the complex numbers c, we can't use a line like the real line, but we have here what's called the real axis, and the vertical axis is the imaginary axis. I'll just write IM for imaginary there. And a number a plus ib is located at the point whose coordinates would be a, b in the plane. So this point where you go out a distance a along the real axis and up a distance b along the imaginary axis is the point a plus ib. And you'll see that the distance of that point to the origin is exactly what we call the modulus of z. Now, I'm skipping a lot of small things about just playing with the algebra of complex numbers to jump to some things which will be very important for us as we study some functions of a complex variable. You all know from Calc 3 that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. And that this will be true for all real numbers x. So we make a definition, we just say that we can create the exponential function with a complex number as the argument, e to the z, just by looking at this exact same power series, only putting the complex number z in place of where we used to have x. We just define this to be the exponential function, and we'll define it to be this for all complex numbers z in C. It's not a difficult thing to see that under a reasonable definition, we can say that this infinite series converges for all complex numbers z, pretty much for the same reason that this infinite series converges for all real numbers x. And just the way we do for real numbers, where cosine of x is 1 minus x squared over 2 factorial plus x squared to the fourth over 4 factorial, etc., we'll define the cosine of a complex number z to be 1 minus z squared over 2 factorial plus z to the fourth over 4 factorial minus z to the sixth over 6 factorial, etc. The standard power series, just like the one you learned for cosine. And for sine, the same sort of thing. Sine of z is z minus z cubed over 3 factorial plus z to the fifth over 5 factorial, etc. And the great mathematician Euler, who worked in the later parts of the 18th century, noticed the following amazing thing. If you plug into the exponential function, not just an arbitrary complex number z, but make it a purely imaginary number, I times some number t, here t is real, so that it is a purely imaginary number, what do you get? Well, when we just plug that into the formula for e to the z, we get 1 plus it plus it squared over 2 factorial plus it cubed over 3 factorial plus it to the 4th over 4 factorial plus it to the 5th over 5 factorial plus it to the 6th. You might wonder why I'm writing so many of these terms down, etc. And then, of course, there's some things maybe I should have talked about earlier. You see that I squared, of course, we already know. That's just -1. But what happens when you look at I cubed? Well, that's I squared times I, so that's -1 times I, which is just minus I to the 4th power is I cubed times, I'm sorry, that should be minus I for I cubed. That's I cubed times I, or another way to think about that is I squared squared. You get back to 1. I to the 5th is then I to the 6th is -1, etc. So it goes in a cycle from I to -1 to minus I to 1 to I to -1 to minus I to 1 as you just increase powers on I. So we can write this e to the it as 1 plus it plus I squared it squared over 2 factorial is like I squared t squared over 2 factorial, which I should write as minus t squared over 2 factorial. Then I cubed is minus I. I'm sorry, so I should write this as minus I t cubed over 3 factorial. I to the 4th is just 1. So then I get t to the 4th over 4 factorial. I to the 5th is again I. So you'll have t to the 5th over 5 factorial. I to the 6th is -1. So you'll have minus t to the 6th over 6 factorial. And then we'll keep going on in this somewhat strange pattern. But then we notice this. If I take, some of these terms are real, some of them are purely imaginary. Real, imaginary, real, imaginary, real, imaginary. They alternate like that. If I look at just the real parts, real terms, I get 1 minus t squared over 2 factorial plus t to the 4th over 4 factorial minus t to the 6th over 6 factorial. And it will keep going like that, alternating with plus or minus signs. So these are all the terms that are real. And then all the other terms are multiplied by an I. So I'll factor out the I. And what do I have left? I have t. Then I get this term minus t cubed over 3 factorial. Then I get a plus t to the 5th over 5 factorial. The next term, which would be the next one coming up there, would be a minus t to the 7th over 7 factorial. And it would keep going like that. And we can write this as cosine of t. This is exactly the series for the cosine function. Plus I times what we have here is sine t. And that's e to the it. And Euler did an enormous number of really great things over his very long lifetime. But this is possibly his most famous result. It's called Euler's formula, that e to the it is cosine t plus I sine t. A very interesting special case of this is what you get when you plug in t equals pi, and you get e to the I pi is cosine of pi, which is -1, plus I sine of pi, which is 0. So you get e to the I pi is -1, or another way to write that is e to the I pi plus 1 equals 0. And this is, again, another famous equation of Euler's, just follows immediately from Euler's formula. And this equation is considered a special one in mathematics because it's a single equation which relates probably the 5 most important numbers in mathematics: e, I, pi, 1, and 0. So there's the imaginary number I, and then 4 of the most important real numbers are 0, 1, e, and pi. And in this one equation, you see how they're all related to each other, which is a pretty astounding thing. Now, that's stuff about the exponential function. We want to talk about the quadratic formula. You all know how to apply the quadratic formula just for quadratics with real numbers. My claim to you is everything works out virtually exactly the same way if you have a quadratic formula and you allow complex numbers for z. The way I'm going to write it here, a, b, and c should all be real numbers. So the coefficients are real, but we're going to allow complex numbers for z, and of course then z squared. If the discriminant of this quadratic, and the discriminant is this term b squared minus 4ac, if the discriminant is positive, all of you know that the quadratic formula tells you there are exactly two roots of this quadratic. In other words, these are the roots of the quadratic equation, az squared plus bz plus c equals 0. And those roots are z equals minus b plus the square root of b squared minus 4ac over 2a, and minus b minus the square root of b squared minus 4ac over 2a. There will be two distinct roots. That's in the case where the discriminant is positive. In the case when the discriminant is 0, this term here is 0, you all know that then there'll be a single root, and that tells you that your original polynomial, az squared plus bz plus c, is in fact exactly a times z plus b over 2a squared. So you have a single root to the equation az squared plus bz plus c equals 0. That comes from this factorization. And that root is what we call a root of multiplicity 2. Now, if the discriminant is negative, in the past you would just look at this in the quadratic formula and say that's impossible, and that there would be no roots to this quadratic equation. But now that we're allowing complex numbers for z, I claim that when the discriminant is negative, just multiply the discriminant by minus 1. In other words, take its absolute value so that 4ac minus b squared is now positive, and the square root of 4ac minus b squared makes sense, and you'll get roots z equals minus b plus or minus I, the imaginary number here, I times square root of 4ac minus b squared over 2a. In other words, you would have these two distinct roots, lambda plus I mu, and I should have said, or lambda minus I mu, where here lambda is minus b over 2a, and this mu is square root of 4ac minus b squared over 2a. What I'd like you guys to do is to check that these two, z equals lambda plus I mu and z equals lambda minus I mu, really are roots. Of the quadratic az squared plus bz plus c equals 0, in that case when b squared minus 4ac is negative. How would you check? You just write down lambda plus I times mu, use the rules for complex number multiplication and figure out what z squared is, and multiply a times z squared plus b times z plus c. Check that it all works out. It's a good exercise if you're not familiar with playing around with complex numbers. So now we have this situation where we can solve any quadratic equation. You'll have two distinct roots in all cases unless the discriminant is 0, which you have one root of multiplicity 2. Now, why do we care about this? Well, we've already seen that to solve a second-order linear homogeneous differential equation with constant coefficients, we can get solutions of the form y equals e to the rt precisely when r is a root of the characteristic polynomial, which is a quadratic polynomial. What we're going to see, and we'll wait until the next day to see this, is that we'll be able to make sense of this even when the number r is a complex number that's not real. That'll happen in the case when the discriminant is negative, so we'll be able to handle that case using complex numbers where we couldn't handle that case with just real numbers alone. In order to prep ourselves for that, I want to talk real quickly about the idea of complex valued functions of a real variable. So let's say we have a function f of t, which doesn't just output a real number, but outputs a complex number. Well, for any t, the output is a complex number, and we can write down g of t to denote the real part of the complex number, and h of t to denote the imaginary part. So we can split any complex valued function of a real variable into a sum of two pieces. One is the real part, and then you have plus I times the imaginary part. When we talk about differentiation of a complex valued function of a real variable, it's very simple. We just write f prime of t is the derivative g prime of t plus I times h prime of t. We just differentiate the real part and the imaginary part separately, and everything works out just as normal. That makes it easy to understand functions like, I'll call it y of t equals e to the, say, a plus ib times t. This is a function of the real variable t. Here a and b are the real and imaginary parts of this number, a plus ib. This is in general a complex valued function. We can think of this as the function e to the at plus ibt. And here's something I didn't mention before, but for this, even the complex valued exponential function, it behaves according to the same rules for exponentials. In other words, we can write this as e to the at times e to the ibt. And using Euler's formula, we can write e to the ibt as cosine of bt plus I sine of bt. So we can make sense of e to, if I think of r equals a plus ib, we can make sense of e to the rt even when r is a complex number, and this is the type of function that we get. And I want you all to check this, but then you can compute that y prime of t if you just differentiate this function, and I've already shown you how you can differentiate things with the real part and the imaginary part separately. I claim it follows the standard rules of differentiating for exponential functions, that you just get the number r, which is a plus ib times e to the a plus ib times t. In other words, the derivative with respect to t of e to the rt is just r e to the rt, and this works when r is any complex number, not just a real number. We'll be continuing with a lot more of this and talk about how this will help us get solutions to more second-order linear, homogeneous, constant coefficient differential equations, all in the next day or so.